Hello. Uh, so this is basically the last topic on polyphase systems. Power factor correction on three-phase systems is not very much different as on single-phase systems. Basically, parehas lang sila. You just want to correct the power factor by adjusting the reactive power using your capacitor bank and or your synchronous condenser. But I guess the main difference here is that instead of uh, dealing with single phase power, we are actually concerned about three phase power. So I have an example here of a three phase system. This is a three phase line with voltage AB as reference. The voltage between each line is 5 kilovolts. Between any two lines is 5 kilovolts. Now it is supplying a load of total power of 2.5 megawatts. So this is basically three-phase power at a total power factor of 0.75% lagging. So we want to correct the power factor to unity using a 300 kilowatt synchronous condenser. Basically, it's essentially a machine that supplies reactive power. So in effect, it's correcting the power factor. Okay, so it's actually easy because of the power triangle. Again, it's not very different from single phase systems. The way you solve for power factor correction using on single phase systems, it's basically the same for three phase systems. So you just the easiest way is plot the power triangle. You have the real power on the real axis, reactive power on the y-axis, and then the total is S load. So this is basically my real power here. This is 2.5 megawatts. This is the power factor angle is arc cosine of 0.75. It's positive because my load is lagging, so it's inductive. Therefore, I have a positive Q load here. So I can actually solve for this Q load here using any trigonometric function. I can use, well, if I use P and theta and the theta, then I'll need tangent. But, well, I can also make way for sine and cosine by solving this S load here. Yeah. Okay, so if your power factor is equal to 1, power factor is basically the ratio of your P over the total apparent power S magnitude. So if it's equal to 1, therefore your total P is equal to the total S, and that makes your Q total equal to 0. So we want to have this Q total of 0 to correct the power factor to unity. So that's what we want. Okay, so as you can see, I have a Q load here. So if I want a Q total of 0, therefore I have to have a Q that is in opposite direction but of the same magnitude. So that's basically this equation. So I can solve for Q load here, and then that is equal to my Q from the synchronous condenser. So that gives me the Q of the synchronous condenser. So yeah, so that's basically the necessary Q if I want to make this power factor equal to 0. Equal to unity or 1. Now if I want to get the power factor of the what do you call this, synchronous condenser, then it's just P of the synchronous condenser all over S of the synchronous condenser, and the S of the synchronous condenser, we can get that from P and Q of the synchronous condenser. So yeah, this is my P, power factor of the synchronous condenser. But this is just a theoretical question. We're not very much interested with that. Okay, now I want to expand this problem. What if instead of a three-phase synchronous condenser, what if I want a three-phase capacitor bank instead? So the idea is, instead of connecting a three-phase synchronous condenser to correct the power factor, I'll be using a three-phase capacitor bank. So I'll still be solving for Q total that is equal to 0, and well, that actually tells me that for that to happen, my Q load must be equal to Q cap, which is essentially 2.2 megavar. There is no pickup real power since this is a capacitor bank, so you don't really have real power there. Now, how do we solve for the capacitor per phase? Capacitance per phase. Well, since this is a capacitor bank, three-phase capacitor bank, therefore we are expecting that we have a capacitor per phase. Now, if you want to solve for the capacitance of each phase, it would actually matter if your capacitor bank is in Y or in delta. This is basically the representation of how you are going to connect your capacitor bank in parallel to the load. This is basically in parallel to the load. This is in delta. This is your capacitor bank in Y, connected in parallel to the load. So let's talk about the delta one first. Okay, so if I want a Q capacitor of 2.2 mVar, that 2.2 is actually three-phase power. So the power per phase is actually 2.2 divided by 3. So that's the power per phase. And this is equal to your V phase I phase conjugate. You can also use V phase squared magnitude divided by Z conjugate, or I phase squared magnitude times Z phase. So if your capacitor bank is in delta, so you have the power per phase. This is the power per phase. And this is equal to V squared over Z phase conjugate. Now, why is this V 5 kilovolts? Take note that if this is in delta, therefore the voltage here in each phase of the capacitor is actually the line-to-line voltage. So that's why this is 5 kilovolts. You can solve for that, and then you get a negative 34.0168 ohms, J ohms, Z phase delta, and that is equal to negative J 1 over 2 pi f c using a frequency of 60 Hz. So that gives you 77.9786 microfarad. So that's basically the capacitor per phase. If the capacitance per phase if your capacitor bank is in delta. Now, what if it is in Y? If it is in Y, take note that you have to consider the V phase here. If that is in Y, the line-to-line voltage here is not equal to the phase voltage because of the capacitor bank, because the phase voltage here, considering that this load is balanced, if this is balanced, therefore we can say that the phase voltage here is just line to line over square root of 3. So that tells you that that is 5 kilovolts all over square root of 3. That's the phase voltage. Okay, and then you solve for this the same way you solve for delta, you get this Z phase. And take note that this Z phase is just Z delta over 3. So actually it's just like your delta to Y conversion. You just solve for the delta and then you convert it into Y. So ganun lang siya. Then you do the same to get the capacitance, you get this value for the capacitance. Okay, so yeah, that's power factor correction on three-phase systems.